Okay, we're going to quickly review isomers, talk a little bit more about chirality and enantiomers, because we're seeing a lot of those with the discussion of carbohydrates. So once again, isomers are molecules that have the same molecular formula, have but different arrangement of atoms or different bonding pattern. Say it that way. Okay? And I'm just going to give you a simple example of this. For example, C3H6Cl2. 3-carbon molecule, we've got 2 chlorines in it. So how many different ways can I draw this? When trying to draw isomers, it is beneficial to number your carbons so you know if you're actually drawing a different molecule. And this isn't something you're going to have to do, but it's just to refresh your memory, your background. I could draw this with a chlorine on this carbon, and hydrogen's here, and I could also draw it or add the second chlorine to that carbon. Okay. So I'm not going to go into the naming of this, but it would be named 1,3-dichloropropane. So I know that's different. So how can I change this? In order to change it, I have to move one of those chlorines somewhere. So I'm going to leave this one on the first carbon and move this one to the middle carbon. Now I do want to point out that if you recall, there's free rotation around these single bonds, so it doesn't matter in what position I put that chlorine here. Okay, but I have moved one atom to a different location. So now I have 1,2-dichloropropene. And then there's one more isomer, and in that one I would have both chlorines on the same carbon. And this would be 1,1-dichloropropane. Okay. So our isomers are primarily going to be enantiomers or diastereomers. So all the carbohydrates have DNL versions, okay, and those will be enantiomers, mirror images of one another. There are D versions in groups of aldoses and pentoses and so forth that have diastereomers. And then, of course, we have epimers as well. But I'm going to first remind you, even though we kind of discussed this with respect to amino acids, chiral molecules contain chiral carbons. And chiral carbons are bonded to 4 different groups. That's what makes them chiral. And we saw that the alpha carbon in our 20 standard amino acids, with the exception of glycine, were all chiral. Okay? So a simple representation of a chiral molecule, I've got a carbon, and it's bonded to a chlorine, a hydrogen, a fluorine, and a bromine, for example. So 4 different groups on that carbon. So this is a chiral carbon. But let's look at the enantiomer D glucose and L-glucose. So we have, of course, the aldehyde head, because these most carbohydrates, with the exception of fructose, have that aldehyde head. And, well, keep going with this one. And there is free rotation around the single bond there. So it doesn't matter which way you draw that. I could have had the hydrogen here, doesn't matter. And then we have our hydroxyl groups. And our hydrogens. And this is the Fischer projection of D-glucose. And I want to reiterate, this is, whoops, forgot hydrogen. This is the way I want you to draw these for me. And I will want Haworth projections for the cyclic structures. So L-glucose is an enantiomer. So pretend this is a mirror. And when I draw the enantiomer, I'm just going to draw the reflection that I would get from that mirror. As so. Remember, the D comes from the side of the chain that hydroxyl group, and in the case of glucose, is on that fifth carbon. Okay? So enantiomers are not superimposable. So I can't slide this molecule over D-glucose and line up these side groups here. Okay. So these are enantiomers of one another. Now I'd like to talk about oxidation and reduction, and we will go back and refresh our memories on that. I'll give you both the organic and the inorganic definitions. Inorganic is quite simply loss of electrons or gain of electrons. Okay. Our focus will be on the organic definition. Which is, gain of CO bonds for oxidation, loss of hydrogen, reduction, loss of CO bonds, C to O, sorry, and gain of hydrogen. Okay. So, since we're dealing, we're going to start with alcohols, although we can oxidize beginning with an alkane. But we're going to start with a primary alcohol because most of the biological molecules are not going to have, going to be alkanes. So primary alcohol, again, the R group representing some form of alkyl group. In a primary alcohol, the hydroxyl group is on an end carbon. And if we subject this to some form of oxidizing agent, which isn't relevant to our discussion, so don't worry about that, we can oxidize that to an aldehyde. So in the alcohol, we had one CO bond, and in the aldehyde, we have increased our C to O bonds. We have two of those now. And in doing that, we also lost hydrogens. We can continue to oxidize this aldehyde head group to a carboxylic acid, in which we have now 3 CO bonds. Okay. So primary alcohols can be oxidized to carboxylic acids. So let's take a look at a secondary alcohol. Secondary alcohols are going to have that hydroxyl group on an internal carbon. And these can be oxidized to ketones. So this is a secondary alcohol with 1 carbon to oxygen bond. And we oxidize that hydroxyl group to a carbonyl, and now we have a ketone which has 2 carbon to oxygen bonds. No further oxidation here. Can't go any further. And finally, just so we're covering all the bases here, if we have a tertiary alcohol, which I doubt we'll see, but just in case, no reaction. Tertiary alcohols cannot be oxidized. Reduction is essentially just the reverse. The reverse. So we will lose CO bonds and gain hydrogen. So we'll be adding hydrogen essentially to these molecules to reduce it in the opposite direction. So carboxylic acids can be reduced to aldehydes, to primary alcohols, and we can reduce the ketone back to a secondary alcohol. And again, the tertiary alcohol, since we can't oxidize it, there would actually be no reaction associated with that. Okay. I thought about covering a couple other reactions, but I think I'll wait until we're actually looking at those molecules. So we're going to move on to drawing cyclic forms of both glucose and fructose. Excuse me, because this is something you're going to have to be able to do. I may ask you for a Fisher projection, or I may ask you for an Haworth projection, and you need to obviously be able to do both. So the way I learned to do this, and I think it's an easy way, if you can't just immediately, so you don't have to memorize it essentially. Starting with the linear Fisher projection, get my rights and lefts mixed up here. So as you've seen on a previous slide, the reaction is going to occur between C5 and C1. And I like to just lay this down on its side, so tip it over. And I'm going to draw it on its side then. So when I tip this over, these are going to have those 3 hydroxyls on the bottom and 1 on top. And it's this carbon that is going to react with that aldehyde head group to form that hemiacetal. Okay. Okay. I don't know what I was thinking there. So we have, if we kind of take a look at this, not quite closed yet, just kind of starting to wrap around. This being C5, C1. I'm not going to draw the hydrogens in there, okay? So there's going to be a rotation of C5 and C6 as that ring closes. And what we get then is the hydroxyl group on C5 essentially, let me get it all down here. Whoa. So here's where that C6 ends up. This is C5. Okay. And we have that, that oxygen essentially attacking that carbon in the aldehyde head group. And when we get the ring closure, then we have here we go. And generally I don't include the hydrogens, and that's fine. You don't need to show me hydrogens, but you do need, obviously, to show me hydroxyl groups. Now, as discussed before, that position of that hydroxyl group could be up or down. If it's in the down position, this is alpha D glucopyranose. Got my Y there, sorry. And if it is in the other position, it is going to be beta. So if it's in the up, we have beta D glucopyranose. Straighten that out for you. All right, so one more, and then you can go back to the video, and then we'll next, after you watch a little more, we'll draw disaccharides. But we're going to look at fructose first, because this is another one that you will need to be able to draw in both forms. This is also a 6-carbon carbohydrate, but it is a ketose. And I take a similar approach to drawing this in a cyclic form, just laying it on its side. And keeping in mind that we're going to have a different interaction, that the ring, we're going to have the carbon 6, or walk through that. Hang on, no, carbon 5. I don't, sorry, I misspoke there. Let's see, 1, 2, 3, 4, 5. I made that a little bit longer. Again, we're going to have these guys. There is going to be that rotation of carbon 6, similar to what we just saw in the cyclization of glucose, but again, it is carbon 5, or that hydroxyl group, that will react with the carbonyl at C2. And when we, as a result, we have carbon 1, carbon 6, this is carbon 5, we have a hydroxyl group here, whoops, and that is cyclic fructose. And of course, again, there's free rotation about this carbon, so we will have either a alpha or a beta fructothyronose here. So that's it for now. You are responsible, as I said, for drawing these structures in both forms, Fisher projections and the Haworth projections.